Dear doctors, I'm Saleh Abdulrahman, a master's student at Baghdad University. The research title is A Proposed Scheduling Algorithm for Real-Time Application 5G Networks. 3GPP and ITU prepared a set of performance requirements for IMT 2020, published in 2017. With the new targets, and due to the higher data rate demand and new applications, 3GPP specified 5G with higher data rates compared to LTE, lower delay time, higher spectral efficiency, lower energy consumption, and others. 5G defined three use cases: enhanced mobile broadband, (MBB), which is the improved version of the LTE high data rate. The second use case is massive machine-type communication, the case of Internet of Things (IoT), where a large number of devices are connected. The third use case is the ultra-reliable low-latency communication, which takes care of very low-latency communication with very high reliability. 5G uses OFDM scheme. In OFDM, there are two domains, frequency domain and time domain. The frequency domain is constructed of subcarriers. Each 12 consecutive subcarriers are called resource block, which is the main frequency domain scheduling unit. The time domain is divided into frames. Each frame is 1 millisecond duration. Each frame contains 10 subframes, each of 1 millisecond. Each subframe constitutes of one or more slots depending on the subcarrier spacing, and each slot has 14 OFDM symbols. The scheduling is a multi-layer process operation, which is responsible for distribution of resources between users. The scheduler in the GMB takes care of the scheduling, takes the information reported by the user equipments, and send control information and time control data to user equipments. The scheduling strategy is not specified by ITU, but it is implementation specific. There are two types of scheduling: dynamic scheduling, where each TTI, the scheduler, defines the available resources and users assigned to by these resources. Semi-static scheduling, which follows a predefined scheme, which does not need dynamic grant, and so it is simpler. It reduces overhead. There are several factors which influence the scheduling decision. CQI, channel quality indicator, which is reported by users to describe the channel quality. Target data rate depends on the CQI, where the better the CQI, the higher the data rate. Average data rate, which is the previous data rate of each user. The lower the data rate, the higher the metric value. Head of line packet delay, it is the time takes for the packet to be sent. So the higher the delay, the higher the metric, so that to avoid packet loss. Queue status and buffer levels, power consumption, spectral efficiency and quality of services. To evaluate the algorithms, several metrics are defined. Fairness is how fair the resources are distributed between users. Throughput is the total data of good and controlled data sent to each user, whereas good put is only the good data after removing the control data. Delay is the time the packet takes to reaches its destination. Spectral efficiency is the amount of data rate per frequency unit. Energy efficiency is the power consumption of the transmission. Block error rate is the ratio of faulty blocks to total number of blocks. Packet loss ratio is the ratio of real-time applications, real-time packets, which are lost due to being late beyond the threshold time specified earlier. The researchers implemented a lot of algorithms. Each has its own advantage and disadvantage. Example of these algorithms is the round robin, which is the most basic algorithm. It shares resource blocks among users equally and does not take CQI into consideration, which makes the utilization of the network is poor. Whereas best CQI targets user equipments with the best CQI. So the result of these algorithms is probably a lower equality between users, lower fairness, and sometimes it results into starvation of users with low CQI. Proportional fair is the balance algorithm between round robin and best CQI. It is the ratio between instantaneous data rate versus average previous data rate. It's considered a very important factor that is used in a lot of algorithms, as you will see. MLWDF, this algorithm is used for non-real-time and mainly for real-time applications. It is three more variables. As we can see, it uses the proportional fair metric beside three variables. The delay of head of line time is the time the packet takes waiting to be transmitted. The delta is the probability of packets allowed to be late, and tau is the time threshold after which packets are considered late. This algorithm uses the delay as a main variable when the delay is zero, or when the delay increases, the metric increases to avoid the loss of packets. Exponential MLWDF is almost the same as MLWDF, but it uses exponential function to give more priority to packets which are late. This will give a higher priority to real-time applications over non-real-time applications, sometimes causes starvation of an RT. The proposed scheduler, as you can see, there are two algorithms, one for non-real time and one for real time. The one for non-real time is the same as proportional fair metric, but for real time, the proportional fair metric combines exponential function of minus log of delta sub I multiplied by delay over 1 minus delay over tau. As we can see, when the delay is zero, the exponential function becomes 1, which makes the metric the same as for real time and non-real time, to give more priority to non-real time application to be compared to real time application. But when the time increases, the exponential function of the real time metric is increases exponentially, which gives a very high metric to real time, especially when the delay reaches its threshold time, the tau. This will give a high priority to real time and to avoid packet loss, as you will see. The simulation done using using 5G air simulator software written in C++ under Linux operating system. Three types of flows are used: the best effort, voice over IP, and video flows. The video flows is of 242 kilobits per second. The maximum delay threshold is 100 millisecond. The drop probability delta is 5 per thousand. Number of users are used here are from 5 to 50 of steps of 5. The results, the throughput, as you can see, two figures for voice over IP and video versus the number of users. The throughput is the total data sent to users. As we can see for voice over IP, almost all the four algorithms have the same data rates. Voice over IP are of low data rate, which makes it easier for the algorithm to process these types of flow with accurate results. But for video flows, you can see that the proposed function gives a higher data rate. That's due to the metric, which gives high priority to real-time flows for video in this example. And to avoid the packet loss, so we get this higher data rates for video flows. For packet loss ratio, we can see that the proposed function, the proposed algorithm, gives almost the same or probably better results for voice over IP than others. For video applications, it gives much less ratio of packet loss. That's again due to the metric that gives high priority for packets, especially when they are late, to avoid the packet loss. It results in very low packet loss ratio for video applications, which uses very high data rates, and especially obvious for higher number of users when the load is high in the traffic, which is considered as advantage for the algorithm. The fairness index for both voice over IP and video, especially for video applications, the proposed function gives higher fairness index than other algorithms, which is an important issue for users where we have higher quality of experience reported by users. Especially for video applications for higher load, the proposed function gives a very high fairness index compared to others, almost 85% for 50 users. For the delay, although the delay is not the lowest delay between other algorithms, but it is not an issue since this delay is less than the specified threshold time, which is 100 milliseconds. This will cause no problem for the algorithm as long as it is less than the threshold time. So this will make the loss ratio less, as we saw earlier. The conclusion, as we saw, due to the construction of the metric and the high priority given to real-time applications by giving them increased metric as the delay increases, we can see that this algorithm, the proposed algorithm, has a better throughput and significant lower packet loss ratio, a higher finish index, especially for video applications. And it is more obvious when the number of users increases, which means the load is very high. The algorithm gives a very good results as the number of users increases and the load is high. While the average delay is within the acceptable range of the maximum threshold, uh, which is specified here as 100 millisecond, as long as it is less than the threshold, it is not an issue. It is okay for video applications and for voice over IP. As a future work, this algorithm may be used in multi-level schedulers, where the scheduler picks uh, the best scheduler for each situation. And in our case, when the situation is about voice over IP or video, especially for video applications for high data rates, this algorithm may be used in multi-level schedulers, while other schedulers may be used for other scenarios. That's the end of it. Thanks a lot, sir.